Welcome, Math 107 students, to the demo for Lesson 22 on polynomial regression. Now that we've studied polynomials and polynomial functions, we can expand the type of regression we can do when we see data points on a scatter plot. So earlier this semester, we were able to enter data into our calculators or into GeoGebra and perform a linear regression, which is the simplest type of regression you can perform. Now we'll see what to do if the data is not linear. So here's a table with 6 data points, and this table shows the number of women in the full-time civilian labor force in millions with children under the age of 6 for selected years. I got this information from the U.S. Bureau of Labor Statistics. So when I see data like this, I quickly would either put it into my graphing calculator, or if I had GeoGebra handy, I would just quickly plot it. And I would take a look at the shape that the scatter plot shows. And in this case, you might say, I can imagine a linear equation maybe coming straight through these points here and fitting closely. And that would be a good model to use for this data. But then I could see someone else saying, yeah, a linear function would be really good for these first 4 points. But look what's happening here between E and F. It looks like it's starting to level off. And someone else might say, maybe some type of quadratic model of function would be a better fit. And just to show you, on your graphing calculators, when you go to the Stat button and you go over to Calculate, you can see that we have a linear regression, a quadratic regression, a cubic, so that would be degree 3, and a quartic regression for degree 4. So those would be the types of regressions you could run, the polynomial regressions you can run using your calculator. Okay, so again, I may want to try both of those and see how well they fit the data. So in part A here, you see that we have fit a red linear function and a purple quadratic function to the data. And both of these are very good fits. When we use regression other than linear regression to look at how strong or how well the data fits that function, we use the R-square value. And the R-square value for the line is 0.96, which, if you recall, when we were studying linear regression, that a number very close to 1 is a very strong fit. And the R-square for our quadratic function is 0.99. So they're both really good fits. Okay, so what I want to just show you right now as we work through this problem, that it's not just, you don't just solely go by the R-square value when you're trying to find a model. Okay, there are other things to consider. So if you were concerned about just estimating, for example, the number of women in between 1975 and 2000 in this data range, so for example 1987, then the quadratic model is going to be the best. But the question is, what if you wanted to predict outside of 2000? Which model should you consider? And that's another whole type of analysis that you need to do. So let's take a look at just working on making some estimates and predictions using these two models. Now, the other thing that I do is I put little hats over my Y value here, and I do that to remind myself that these equations are estimates of each other. So the equation for my regression line, I can read right off the graph. And the equation for my quadratic function, I can read right off the graph. Now that we have both of those equations, we can move on to the second question here in part B. So what I'm going to do is we'll read it and then we'll go back and fill in the value of x into our equation and we'll get our prediction. So use both models, the linear and the parabolic, to predict the number of working women with children below the age of 6 in 2011. Which model seems like a better predictor? So 2011 now, recall that 2011 is outside of our data range. We're going out into the deep unknown. It's beyond our data range. And remember, both of these models are for the data that we know. So we always have to be careful when we go too far outside of the data range. And if you may recall that we call that extrapolation. So when we find the values for 2011, this is an example of extrapolation. Extra, we're going into the extraterrestrial world, extrapolation, okay? So we have to find our value for x, and x here is determined by the number of years after 1970. So 2011 minus 1970 gives us 41. So x equals 41 in this case. So what we do is we go back to our models and we substitute x equals 41 into each model for x. Oops, I put my decimal place in the wrong place here. It should be 3.9919. That would have made a huge difference. I'm glad I caught that. Maybe you caught it while you were reviewing this. Y, oops, let's go to the purple. Y hat equals negative 0.0048 times 41 squared plus 0.3799 times 41 plus 2.8662. So let's take a look at both of these in our calculator to see what each function predicts, what each model predicts for the number of women in the workforce in the year 2011. So let's take a look here. 0.2111 times 41 plus 3.9919. That's 12.647 million women. So my prediction for in 2011, there will be approximately 12.6, my calculator keeps coming off the screen, 647 million women in the full-time civilian workforce with children under the ages with ... And we remember we're using a model here, so this isn't the actual number. So what I always encourage students to do, in case you forgot about this, is I always start off these sentences with according to the model. According to the model. So that tells your reader and yourself that this is either an estimate or a prediction based on a model. So according to the model, in 2011, there will be approximately 12.647 million women, blah, blah, blah. Okay, let's see what we get with this quadratic model. So as we look at this line and we think about going out 41 years, we can see that the linear regression will predict a value higher than our quadratic regression. So we should be expecting a value here for y hat that is smaller than 12.647. So these are all the things you can do just to make estimates before you actually go about doing the arithmetic so that just in case you made a mistake somewhere using your calculator, you would be able to figure that out. So let's put in the 41 and square it. And we're going to add 0.3799 times 41. And then we're going to finally add 2.8662. Okay, so we can see here that that comes out to be 10.3733. So y hat here is 10.3733. 3733. So again, you could write your sentence according to the model. And you may even be more specific. You could say according to the quadratic model, and over here you could say according to the linear model. Okay, and then we can complete our sentence. Approximately 10.3733 million women will be in the workforce in 2011. So over on your next page in your notes, you could put both of those values in here, 12.647. Don't forget your units, millions, and 10.3733 millions. Okay, so it's always important to make sure you have your units. All right, so the next question says, use the leading coefficient test. Remember, that was from study of polynomial functions to determine the end behavior. So this is the other thing you need to consider when you're picking a model, is the end behavior, not just the R-square values that we talked about initially here. The end behavior to the far right for each model. Which model do you think would be most accurate in modeling the future number of women in the civilian workforce? Let me just say right now that you could, at least depending on how far out into the future you wanted to go, you could make an argument for both. But if we talk about strictly the end behavior for the linear function continues to rise. And strictly speaking, the end behavior for this quadratic function is falling, and eventually will be negative. So if we're strictly speaking about end behavior, then we would say that the linear model, the end behavior for the linear model, would be a better predictor. For modeling the future number of women in the blah, blah, blah. Okay, you can finish that off. So we're strictly looking at many, many years into the future, and we don't know what sort of social, economical, or cultural factors are going to affect the number of women with children under the age of 6 in the full-time workforce. So as you can see, there's a lot of different variables, no pun intended, that can affect this model, and perhaps neither of the models will be useful then. I just want to tell you a little secret. I did look back into the table for the labor, the number of women in the labor force in 2011. And what I recall seeing was that it was 9.268. So this model of the quadratic function, where it's actually going to start to decrease, would have been a better predictor, at least for, another 11 years out of this data set. However, remember, we were just talking about end behavior, and we can't have negative women. So it's tricky. It's tricky. So mainly the idea that you want to have in your head when you consider these things is, What do I think will happen in the future when you're trying to decide which model? That will be end behavior, knowing that you're running into dangerous territory. And when you're trying to figure out dates, in this case, any year between 1975 and 2000, here you'd want to use, say, your quadratic function because it is a better fit. It's closer to those points. So remember, when you're trying to make a prediction or an estimation within a data set, between the numbers in your domain, that's called interpolation. So we've tried to summarize all of this into the next few steps here for you. So here's a 4-step modeling process. You want to always create a scatter plot of your data, decide whether a line, a parabola, or some other type of polynomial curve of higher degree comes close to the points. And remember, all we have available with the graphing calculators are cubics, which are degree 3, and quartics, which are degree 4. The more peaks and valleys the data has, the higher the degree of the polynomial needed. Find an equation of your model choice, and then let the calculator or computer take care. We let the calculator or computer take care of this step for us. Verify that your equation has a graph that comes close to your points in the scatter plot. If it doesn't, check for typos or calculation errors. An alternative to reconsider your choice of model at step 1. Sometimes you think you might have a good fit by picking a model, and then once you see the graph of that model on your scatter plot, you say, I think maybe I can do better. Use your equation of the model to draw conclusions, make estimates, and/or predictions, because the end behavior of a higher degree polynomial rapidly tends to either positive or negative infinity. Extrapolation-based predictions are usually inaccurate. Extrapolation is subject to higher risk of producing meaningless results. And as you recall, those meaningless results had a name. The meaningless results was called model breakdown. Discussed that way back in like a second or third class lesson. All right, so how do you actually select a model? At the beginning of the modeling process, we must decide whether a linear, quadratic, cubic, quartic, or none of these is suitable for modeling a situation. Here are some criteria for selecting a model. Now, these are just guidelines. There's like no exact science here. The graph of the model should fit the points well. Use the simplest model that captions the pattern of the data. So if you had a choice between, say, a 4th degree polynomial and a line, and they both fit well, take the line. Use the line. The model should make sense within the context of the real-world situation. So if your end behavior is going to quickly go to a negative result, then you wouldn't use that model. So you're going to have a chance now to practice all of these ideas in the activities, which we'll talk about in the next video. But the other thing I just want to relieve any tension you might be feeling is we're not going to ask you to put this into your calculator or into GeoGebra. We will give you all the equations that you need and the graphs for you to discuss, okay? Discuss and think about. Okay, that's it for lesson 22 demo. If you have any questions, as always, feel free to send me an email.